Page number 8 of your procedure gets into the actual procedure. So this has your protocol and how it's lined up. The way that you're going to start this protocol is first by evaluating this small beaker. Now this small beaker has a maximum volume of 100 milliliters. What we are going to do is we are going to fill this to 100 milliliters. Then what we are going to do is determine the mass of this beaker when it's filled with water. In order to do that, I'm going to use the large beaker just to serve as basically my receptacle that holds lots of my solution. So what I will do is I'll fill this up, transfer up to 100 milliliters, and then put it on my digital balance to tell me the mass of this. But before I do that, if you flip over to page number 11 of your procedure, you'll see that we need to basically come up with what's the mass of this small beaker. I'm going to provide you with that data. Then, when we fill this up with approximately 100 milliliters of water, what's the mass of it? Then, what's the mass of the water in my small beaker? And then what is the volume of water in my small beaker? So the mass of water is going to be determined from my digital balance. The volume of water in my small beaker is 100 milliliters. After I do that a total of 3 times, I'm going to be able to look at my calculations and see how accurate this piece of glassware is. Next up is using my volumetric flask. Now this has a slightly different volume because it has a maximum capacity of 50 milliliters. So this volumetric flask has a mass to it. I'm going to determine what that is, provide you with that. Then you're going to fill this up with deionized water. Fill it to that line as carefully as can be done. Then determine the mass of water in that volumetric flask and what's the volume of water in that volumetric flask. Again, the volume is going to be 50 milliliters. Now what you're going to do once we have completed this for all 4 of our pieces of glassware, the Erlenmeyer flask as well and the graduated cylinder, is you're going to do some percent error calculations. Now, a percent error calculation is demonstrated at the bottom of page 9 of your experiment. So, a percent error calculation shows shows 2 lines displaying an absolute value. And then within that you have a division calculation, which is experimental value minus theoretical value divided by theoretical value. The values that you're going to be inputting there are the densities, because we're comparing our calculated density to our theoretical density. Our theoretical value's density is 1.00 grams per milliliter, or 1.0 grams per milliliter. And that's going to be what it is for every single trial. Because our water isn't changing, we're not going to any increased altitude or anything like that. So that theoretical value will be the same in each calculation. Right here and right here. Now the experimental value. The experimental value is something that you are going to collect from each one of your trials. You're going to say, based on the mass and the volume of my sample, mass and volume of water in each one of my trials, what's the density of water that I've determined? It should be close to 1, but you're going to say whatever it is, minus 1.0 divided by 1.0, then you're going to multiply that by 100, because that will give you the percent error, basically the accuracy of your results. You'll do that a total of 3 times for each piece of glassware, and then you'll determine the average percent error of a small beaker. At the end of the procedure, after you've looked at all 4 pieces of glassware a total of 3 times, then what you do is you have a couple of different pieces of glassware, a couple of different reflections. So the first reflection is which piece of glassware had the highest percent error. That is going to be determined simply based on the results that you collected. Number 2, if you wanted to make ice cubes, which piece of glassware would you use to transfer water from your faucet to the ice cube tray? Why? Think about how precise and accurate you would need or want your measurements to be for this scenario. So think about when you're filling an ice cube tray with water. Are you really carefully measuring out the volume that you need? I personally don't. So think about that with respect to your different pieces of glassware. Next up, if you wanted to make cookies, which piece of glassware would you use to collect water to transfer into your mixture? Why? Okay, so this is something that you're a little bit considerate about the accuracy of your measurements, because if you try to cook something and it doesn't really land properly, it might not taste very good. So that might be a little bit skewed. Number 4, if you wanted to prepare a saline solution, so a saltwater solution, to wash your or someone else's contact lenses, which piece of glassware would you use to make this solution? Why? Okay, so now thinking about this, a saline solution, what's the role of that? It's to clean the contact lenses. So it's really there to kill some bacteria, wash away any junk that are on those contact lenses, that is on those contact lenses. So, but also, it's dilute enough that it's not going to leave a bunch of salt on those contact lenses. So that's something that, you know, my eyes are pretty sensitive, and if I got some salt water in my eyes, that might sting a little bit. And so you're kind of comparing, like, how carefully do you have to do that compared to, you know, the making of the cookies. Okay, the 16th page of your procedure shows your last 2 reflections. Would you expect your density calculations to be different if you did not have a digital balance for your procedure? Would this impact any pieces of glassware more so than the others? Okay, so if you didn't have a digital balance, then you'd have to have some other means, like what's known as a triple beam balance. So your accuracy might be a little bit distorted. If you didn't have a digital balance like what we're using, maybe you could find a balance that you would use in like a kitchen or something like that. Those are not nearly as accurate as our digital balances that go to 2 decimal places. And then the last reflection is based on your data, not your perception or your gut feeling of these different pieces of glassware. Based on your data, which piece of glassware is most accurate or is best for making accurate measurements to the worst? So you're going to rank them based on the accuracy that you observed. All right, well, I hope this was helpful. Have a good day.